Hey everyone, in this video I'll be going over the problem statement, intuition, algorithm, and runtime for Dijkstra's. So whenever we see some sort of graph algorithm, I think it's first important to understand what problem that algorithm is trying to solve. So the problem that Dijkstra's algorithm is trying to solve is that we want to find the shortest paths from a given start vertex to all other vertices in the graph. So what do I mean by that? Well, let's say that we have some start vertex A. So Dijkstra's algorithm wants to solve the problem of finding the shortest path from A to B, from A to D, from A to C, and from A to E. Okay? In essence, we want to find, hey, for any vertex in this graph, what's the shortest path from A to that vertex? All right? So let's start trying to build an algorithm together. So if we're trying to find the shortest path from A to any one of these vertices, which is the easiest vertex we could find the shortest path to? The first one. Well, it seems to me that's probably C, right? Because C is like the closest vertex to A from the start. So I can see that like the shortest path from A to C is probably just going to take this edge here. All right. So it turns out that the intuition for Dijkstra's algorithm kind of leverages this idea and just keeps building upon it. So more specifically, the intuition for Dijkstra's is that we will keep visiting the next closest vertex from A, all right, where A is our start. All right, so that is actually most of the intuition behind Dijkstra's algorithm. So from the beginning, what we know about A is that it has three neighbors, C, D, and B. And one thing I want to note here in Dijkstra's is that initially, we don't know anything about how far other vertices are. So what I mean by that is that we learn information about the other vertices in the graph as we visit more vertices. Okay, so if this doesn't make sense, let me kind of explain. Initially, we know nothing about this graph. Then my claim is that let's first start off by going to A. So when we go to A, we learn information about the neighbors of A. More specifically, we kind of realize that these three gray edges exist in the graph. Beforehand, we don't know anything about the graph. So after we go to A, we learn that these three gray edges exist here. Okay? Then, after I go to A, I'm going to realize that C is the next closest vertex. So let's go to C, right? So after I go to C, I learn information about these two gray edges here, right? And that information can maybe tell me where the next closest vertex will be, right? So as I keep visiting more of these vertices, I learn information about more edges in the graph, and learning information about those edges can help me find the next closest vertex to go to next. All right, so that's in essence what Dijkstra's algorithm really just does. So I'm actually going to kind of rephrase this and say, when we visit a vertex V, we learn information about the neighbors of V. All right. So when we go to C, we learn information about the neighbors of C, right? And what I'm going to do now is I'm actually going to take one step further, and it'll be helpful for us to try to keep track of this information that we learn, right? So we're learning information about the neighbors of V, right? So we should have some sort of way of storing that information, right? So what I'm going to do is that for every vertex, let's do it up here. For every vertex, we will keep track of two things. All right. So the first thing, let's put it in orange. The first thing we're going to keep track of, I'm going to call it dot dist, and it's going to be the closest, maybe this, yeah, closest recorded distance from the start. Okay, so that's the first thing we're going to keep track of for every vertex. The second thing that we're going to keep track of for every vertex, let me give myself a little more room here. Let's change colors too. Let me see how many colors I can use today. Okay, so the second thing we're going to keep track of is I'm going to call it dot back, and it's going to be how we got to a given vertex. All right, so kind of looking at this graph here, if we're looking at C, the distance from A to C was 1, right? That's the closest recorded distance from that vertex to the start. So I'm going to put a 1 here to keep track of that. And how we got to C is from A. All right. For all of the remaining vertices, actually, before we go to C, for the vertices BD, we know that after I start at A and I look at B, so I'm going to say that currently the shortest distance from A to B that we know of is 5, and how we're getting to B is from A. Okay? Additionally, the shortest distance from A to D that we know of before we go to C is 4 via this edge, and we got there from A. Okay, so after I visit A, I know all of this information, right? And I also can say here that I don't really know anything about E because we haven't seen any edges neighboring E yet. So I'm just going to say that E is currently infinity away, and we don't really know how to get to E, so I'll just put a dash here. All right. So then when we visit C, we learn information about the neighbors of C, right? More specifically, we kind of learn that these two edges exist here. And what we'll realize is that this is a shorter path of getting to D than what we previously recorded. So what I'm going to do is update these values to reflect that. I'm going to say the new shortest distance to get to D is 3, and how we got to D was via C, right? Then what I'll say is that for E, I can also update that. So I'm going to say that the new shortest distance to get to E is 10 via this path, and how we got to E was from C. All right. So out of these three vertices, we'll notice that C is the next closest vertex from our start. So let's go to C. All right. So after we go to C, we learn information about the neighbors of C, right? More specifically, we kind of realize that these two gray edges now exist in our graph. So what we're going to do is we're going to ask ourselves, is this a better path of getting to B than what we previously recorded? Well, this path is of total length 6, but we already knew a way of getting to B of total length 5, so we're not going to update B because the values we had here were already better than this new path, right? So when we're looking at E, what we'll notice is this path of getting to E is of cost 9, which is better than 10, so we can update both of these values to be 9 and D respectively, right? So I'm going to kind of get rid of these gray edges for now, because now we've seen the entirety of this graph. So the next thing to do here is let's go to B. And I'm going to kind of go quickly here, because we don't really learn any information after going to B. So then we'll go to D, or we'll go to E, right? So, oops, I kind of messed this up. This should be this edge right here, because that's the better way of getting to B. All right, so yeah, we ran Dijkstra's. Good job, everyone. So the first thing, or one thing I kind of want to note here, is that after running Dijkstra's, we get something that I like to call, or actually not I like to call, like that is called the shortest paths tree. So what exactly is the shortest paths tree? So the first kind of step here in understanding this is, what is a tree? So a tree is a connected acyclic graph. So connected means all the vertices are connected. That means from any two vertices, we can get from that vertex to the other vertex. That's what connected means. Acyclic means there's no cycles in the graph. All right. So this tree is a shortest paths tree. So that's what a tree means. It turns out that the shortest paths tree is a special type of tree. So this is actually something that we can call a spanning tree. So a spanning tree is a tree. I like to think about it inside a graph that touches all vertices, right? The touches all vertices kind of comes from the word spanning. It spans the entire graph. So the shortest paths tree, kind of recapping, it's a tree. What is a tree? A tree is a connected acyclic graph. On top of that, it's not just a tree, it's a special type of tree called a spanning tree that is a tree that lives inside of a graph that touches all vertices. So we can kind of see here that this is a tree, right? It's connected, all vertices are connected, and it's acyclic, there's no cycles here. And the reason it's called a shortest paths tree, right? Where does this kind of come from? Is that to find the shortest path from A to any vertex, we can just traverse edges. Okay, give me a sec. I'm going to try to give myself a little room here. No. Okay, last try. All right. So to find the shortest path from A to any other vertex, we could traverse edges in the shortest paths tree. So SPT is just a short form for shortest paths tree. So kind of recapping what we've done so far, we've done a lot. So we've understand the intuition behind Dijkstra's is that we keep visiting the next closest vertex from A, which is our start. Initially, we don't know anything about how far away the vertices are, and every time we visit a vertex V, we learn information about the neighbors of that vertex, right? So we learn this information, but we need to keep track of it somehow. So to keep track of this information, we keep track of two things for every vertex. I call one dot dist, which is the closest recorded distance from the start, and the second is dot back, which is how we got to a given vertex, right? So after running Dijkstra's, we kind of get this shortest paths tree, and how we actually encode this information in the shortest paths tree, this information is actually all encoded in the dot back variables for every vertex in the graph, right? Since we know that we got to E from D, then in order to find the shortest path from E to A, I could just kind of keep going backwards, right? I got to E from D, I got to D from C, I got to C from A, right? So you can kind of think about for yourself that these dot back attributes comprise, or they give us the information of the shortest path tree, all right? So with this in mind, let's think about how we could translate this into an algorithm, all right? So I kind of written the start of the algorithm. So for every vertex v, let's start off by kind of writing some of this information down in its initial form, right? So initially, we don't know how far any vertices are, so we're going to say their distance value is infinity. We don't know how to get to any vertex initially, so we're going to say its dot back is null, all right? And then what we're going to do here is that we can say the distance to get to start is 0, because we know that start is 0 away from start, even from the beginning, all right? Now, the next thing I'm going to do is I'm going to create a priority queue, all right? So if you guys kind of recall, a priority queue is a heap, right? Or more specifically, a heap is the data structure that implements a priority queue, right? So if you kind of recall, a priority queue is a collection of items, and at any point in time, I can retrieve the item of highest priority. So why does that kind of tie into Dijkstra's? Well, if you think about it here, looking back at our intuition, in Dijkstra's algorithm, we keep visiting the next closest vertex from A, right? So in order to keep visiting the next closest vertex, you can kind of think about that the priority of a vertex is how far away it is from A, right? So if I create a priority queue with all the vertices in my graph ordered by their dot distance values, that means that at any point, if I remove a vertex from my priority queue, I'll be removing the next closest vertex to A, right? So I'm going to kind of write that down here because I think it's really important, is that at any point, if I remove a vertex from the priority queue, so we also call the priority queue a fringe. So I'm just going to call it a fringe going forward. From at any point, if I remove a vertex from the fringe, it will be the next closest vertex from A. All right, so that's the intuition behind a priority queue. All right, so now we've kind of like instantiated the data structure. We've kind of put the default information for every vertex. So let's move to actually implementing this kind of logic here, that we want to keep visiting the next closest vertex. And we also want to somehow implement this idea here, that when we visit a vertex, we learn information about its neighbors, right? So that is going to kind of come in this section right here, and this is actually the rest of the algorithm. So what we're going to see here is while the fridge isn't empty, what this is saying is that while there are vertices yet to visit, right? Then what we're going to do is we're going to remove the smallest from the fringe, which, as I kind of talked about here, that is going to be the next closest vertex from A, right? So P is the current vertex we are visiting, and it happens to be the next closest vertex from A, right? So now what we're going to do is we kind of want to implement this idea here, that when we visit a vertex, we learn information about its neighbors. So that comes in right here. Okay, so what we're going to do is we're going to look at every neighbor of P. All right, so Q is every neighbor of P, where P is the current vertex, right? So what we kind of do is we consider every neighbor Q, and we know that there must be some edge between P and Q if a Q is a neighbor. So we're going to say the weight of that edge is W, all right? So now what we're going to do, I think this if statement is really important here to understand. And what this if statement is saying is that if we found a better way of getting to W. Okay, so that's exactly what this if statement is saying. So let's kind of break it up into parts. So q.dist was the previously recorded distance of getting to Q, right? Recall what .dist is that it's the closest recorded distance from the start, all right? So initially we thought Q was this far away from the start. Well, what if it turns out that the distance to P plus the edge from P to Q is smaller than the previous distance to Q? All right, so what do I kind of mean by that? Well, kind of remember that when we were visiting D, or when we were visiting C, right? At this point in the algorithm, D was 4 away, and we said in order to get to D, we came from A, right? Because after visiting A, we saw that D was 4 away. So now what we'll notice is that when we go to C, we learn information, right, that this edge between C, D exists. More specifically, we realize that this path is a cost 3, which is smaller than 4. So we want to update both of these to 3 and C, right? So notice here that if I say that C is currently, let's say C is currently my P, and let's say D is currently my Q, kind of using the variables back in the algorithm. And if you're kind of considering that this is the edge between them, which is of weight 2, what we'll notice is that p.dist is this value 1, plus the weight of 2 is smaller than q.dist, which was 4, right? So if that doesn't make sense, kind of coming back down here, recall that what we're checking is if q.dist, which is how far away we thought q was, if it turns out we found a better way of getting to, oops, this should be getting to q, that's completely my bad. All right, so if it turns out we found a better way of getting to Q, right, via P, then you know that P.dist plus W is smaller than Q.dist, right? So if that's the case, what we did up here is that we updated these two values to reflect the newfound information, right? That this path is better, and in this path we came from C. So we'll do that update right here. We'll say that Q.dist is equal to P.dist plus W, and in order to get to Q, we came from P. Yeah, so that's the entirety of Dijkstra's algorithm. I think the last thing I'm going to do in this video, I know it's kind of long, is I want to touch upon the runtime. All right, so whenever we're considering the runtime of some sort of graph algorithm, we want to determine where all do we do data structure operations. Okay, so let's kind of look back at the pseudocode. And I'll be honest, the pseudocode doesn't actually show all the data structure operations that are happening. So we'll have to like kind of look a little between the lines. So we know that we have some priority queue, right? That's the main data structure of Dijkstra's. So in this priority queue, let's see what operations we do to the priority queue. So the first thing that we kind of do is in the priority queue, we have all of the vertices initially. So I'm just going to say here, we have to add all the vertices to the priority queue. All right. Then we also remove every vertex from their priority queue. So we have to do a remove operation as well. We'll say remove smallest. So the last operation is actually kind of subtle, but it's a change priority operation. So kind of notice here that when we update these values, that our priority queue is ordered by the .dist values of the vertices. So if I update a vertices .dist value, it means that we change that vertices priority, and what we need to do is kind of bubble that vertex up or down, right? We're probably just going to like have to bubble it up because its priority went down, right? So what we'll notice here is that we have to do change priority operations whenever we update a vertex's priority, right? Which happens when we find a better way of getting to a vertex queue, right? So these are three operations. So now what we'll try to do is how many times do we do each of these operations? Okay, and I'm going to let E denote the number of edges in the graph, and we'll have V denote the number of vertices. All right, so I'm going to say that we have to do V add and V remove smallest operations because we have to add every vertex and we have to remove every vertex. So if you think about to yourself that like if we're adding all the vertices with like initially infinity priority, maybe we don't actually have to do this, so we could save on the runtime. It turns out this term doesn't really matter overall. So yeah, we could also equivalently get rid of this, and it would be the same thing if we choose to add vertices upon seeing them. All right. So the last thing here is how many change priorities could we do in the worst case, right? So let's look here. In the worst case, every time we see some sort of better path of getting to Q, we have to update that vertex's priority, right? So notice that we could execute this for every edge. All right. So the intuition of why we could execute this for every edge is suppose that we have some sort of edge in the graph, right? Like let's just say this random edge here. So if it turns out that every edge gives us a better way of getting to a given vertex, that means that every edge in the graph leads us to do this update, which leads us to do a change priority operation, which tells us that the maximum, this is the maximum number of change priority operations I can do is E. So this gives us the runtime. Oh shoot, we're missing one final thing actually, is how long do each of these operations take, right? So we know that a priority queue is backed with a heap. So a add operation, actually all operations in a heap for that matter, all take log time, right? Well, how many elements are in the priority queue? Well, we can say that there's going to be V elements in the priority queue at a time, right? Because V is the number of vertices in our priority queue, we have V elements. So our runtime becomes V log V plus, let's do 2 V log Vs for adding and removing, though we can kind of get rid of one because they're like the same term. It becomes V log V plus E log V when we multiply these two together. The reason we're multiplying here is that a change priority operation takes log V time, and we do E of them, so it gives us E log V. So runtime becomes V log V plus E log V, which we could simplify to V plus E log V. And if it's the case that our graph is like pretty connected, we can even simplify this to just E log v, assuming that we have at least as many edges as vertices. And I think it's important to put a bound here, so we're going to put a big O bound. So both of these are equally valid. The second one just assumes that we have at least as many edges as vertices, because in order to run Dijkstra's, we assume that we can get to every vertex, so there must be at least as many edges as vertices. So yeah, and that is all for this video walkthrough. I hope you all found it helpful, and yeah, stay tuned for the next ones in the series.